All right. So derivative. So you have practiced and we learned getting a derivative by definition or by ab initio. And now we are going to deduce some rules or introduce some rules so that you don't have to use that cumbersome method all the time. That's important to learn the concept.
आवाज खत्म होगी
नहीं सर सही आ रही है सही आ रही है
सर सही आ रही है सर सही आ रही है
वॉल्यूम ऊंचा करना
सही आ रही है सर सही आ रही है
That's important to learn how the derivative is defined, but for operational purposes in practice we usually do not use that method. So even in this setting, in this class, unless you are explicitly asked to take a derivative using first principles, using ab initio or by definition, then you should use that difficult method. Otherwise, you can use the simple rules that I'm going to introduce today, and we're going to learn to take the derivatives. The first rule is about the derivative of a constant. So if you have a function which is equal to a constant, the derivative of a constant. So what a constant function looks like? A constant function looks like this. X, you have f of x, and in this case f of x is equal to k. K has some value, so it is nothing but it has a constant k value. Okay, and since we know that derivative is rate of change of the function with respect to the variable, is this function changing with respect to the variable?
No sir.
No sir.
So the
No, sir.
rate of the change, just let's make the non-verbal response here, please. So the rate of change, it's not changing. So the rate of change is 0. So is the derivative. Derivative of a constant alone is always 0. One of the first rules, there is another rule, f of x. Let's say you have a function which is defined as f of x to the power n, where n is any power. These Safi?
सर इसका जो पहला वाला आपने बताया है इसका डेरिवेटिव 1 नहीं होना चाहिए
नहीं, क्यों
सर देखिए ना, अगर k की पावर 1 है तो वो 1 जब हम लाएंगे तो उसकी पावर 0 हो जाएगी, तो वो आंसर 1 नहीं आना चाहिए.
K is not a variable. K is a constant. The variable is x. The variable, look at the x-axis. The variable is x. F is defined as a function of x. K is just a general variable. General constant. I haven't specified its value, but it's a constant. Okay. So f of x to the power n, you can show this derivative. I'm not going to show using the first principles, and also verify using few powers of x is always equal to n to the x n minus 1. So sorry, d of f over dx. This is the second rule, and these are short forms you can always use. Any question about this? Okay. For example, we did this in the, sorry about this, the box should include the power. For example, if you take the derivative of, if f of x is equal to x cube, I think we did this example in the class last time, d of f over d of f is equal to px2. You can verify this using first principle. You can verify this one using first principle. Okay. The third is when a function is multiplied by a constant. Let's say we have f of x, which is a constant times an other function g of x. Okay. And its derivative would be d of f over dx equal to k d g over df. Please keep your mics mute.
नदी आपका माइक ओपन है.
Keep your mics mute, please. अगर अली अगर आपका अब कोई और सवाल नहीं है तो ये हाथ नीचे कर लें. So this, for example, it looks very difficult to make sense, but think about this function for this third. So if you have f of x equal to 5x squared, but we can always write this f of x equal to 5 g of x, where g of x is equal to x squared. Okay, see this, f of x is equal to 5x squared. So take the constant out and substitute with the g of x, where g of x is equal to x squared. So whenever you have a situation like this, when you apply the derivative, you can always take the constant out and apply the derivative to the rest of the function. Okay.
Sir, won't it then be k derivative dg over dx instead?
Oh, yes, sorry. Yes, and I'm sorry. Yes, thank you.
तो सर 5x स्क्वायर का फिर डेरिवेटिव 10x नहीं होना चाहिए.
जी बिल्कुल. तो वो देखिए आप, ये सारे ये जो 2-3 रूल्स हमने किए हैं, इसको आप अप्लाई करें 5x स्क्वायर्ड पे. ठीक है. तो पहला रूल हमें कह रहे हैं कि आप ये वाला जो लास्ट हमने the third one is saying you can take the 5 out and take the derivative of the rest. So let's take the derivative of the rest. Okay. df over dx. So 5 outside, and the derivative of the rest of the function is x squared, and that would be 5 times, and that's 2x, right? And the final answer would be 10x. Okay. All right. The fourth rule is the derivative of the sum is equal to the sum of the derivatives. So if you have a function which is the sum of two other functions, the derivative of that function would be equal to sum of the individual derivatives of those functions. Okay. So an example would be if you have f of x is equal to 2x cubed plus 3x squared. You see this? You can take this as first function and as the second function u, and if you need to take the derivative of this whole expression, you apply the derivative individually to these, and then once you come to these are covered by the earlier rules that we have defined. Okay. the product rule. So if you have a function, this is a bit more, you have to be a bit more careful because the previous rules were simpler. So if you have a function which is product of two other functions, in that case, this is what the derivative of f of x would be. D of f, d over x. So the first function as such multiplied with the derivative of the second function plus the second function as such multiplied with the derivative of the first function. Right? So this is the sum rule, this is the product rule, okay, and then we have the chain rule.
सर क्वोशिएंट रूल नहीं है
जी
सर क्वोशिएंट रूल नहीं है सिलेबस में
वो क्या है?
सर जो डिवीजन वाला है
अभी मैंने सारे रूल्स किए नहीं है, आप उसके बाद पूछो. So we have chain rule which says that if you have a function of another function, so let's say f is a function of y and then y is a function of x. Okay, so we have a function of a function. So f is a function of y and y is a function of x. Okay, so if we have this situation, then we can take the derivative of f with respect to x using this rule. Df over dx equal, first the derivative of f with respect to y, okay, multiplied by the derivative of y with respect to derivative of x. This is chain rule and it doesn't stop at just two functions. You can continue. Let's say that x is a function of time, okay, t, or another variable. Then this would be a three-way chain rule. Y is a function of, f is a function of y, y is a function of x, x is a function of t. And then in that case, the chain rule would extend to three terms. The third term would be dx of dt. Okay? So this
हम df over dx को भी t कर देंगे.
what I'm saying is that we have a function of a function, but it doesn't have to stop here. I can have a function of a function of a function. Okay, so I can have three layers of this problem. And in that case, then we'll have three terms here. And I'm saying my third x, let's see, f is a function of y, y is a function of x is a function of t. And in that case, if I want, so the one thing is very important, this would change here. So if I want to take the derivative of f with respect to that final variable, t, the last variable, then I can calculate, let me write that as well for three variables. Then this would be df over dt equals df over dy, dy over dx, and dx over dt. See this? And it still doesn't have to be, it can extend for a fourth term, a fifth term, a sixth term.
So we can keep this going for an arbitrary number of functions.
G?
So we can keep this going for an arbitrary number of functions.
Yes, yes. Yes, you can. So this is chain rule. And the last one is when you have a function divided by a function. You have f of x equal to u of x or b of x, then the derivative would be, again, the first, the function in the denominator as such, the derivative of the function in the numerator minus the derivative, the function in the numerator as such, the derivative of the function in the denominator, all divided by the square of the function in the denominator. All right. So these are few of the rules that you can use in shorthand, and I mean to do derivation very quickly. And I think that's all I have to say about derivatives. So if you have any remaining confusions, questions, go ahead and ask. Can you repeat the last rule? So if you have, let's say you have a function that looks like x squared over sine x, okay? And if you want to calculate the derivative of this function with respect to x, so this is what the derivative would look like. I'm applying this rule, sine x, and I'm going to evaluate the derivative of this now. So this would be, let me just write without evaluating first, d x squared over x, that's my function in the numerator, minus x squared as such, the derivative of sine x over dx, and all divided by sine x squared. Okay, so this is an example of the last rule. Is it better now?
Yes, sir. Thanks.
Okay, an example of chain rule. Okay, let me think of an example of chain rule. F of x is equal to y squared and y is equal to x cubed. Okay, now this is y of x is equal to x cubed. Now this is an example of chain rule. I have two functions. So f is a function of y, and then y is a function of x. So in this case, we want to take the derivative, the chain rule. The definition of chain rule is, where is the definition of chain rule? This is the definition of chain rule here. Okay, see this? First, the derivative of f with respect to y, and then the derivative of y with respect to x. So we'll apply chain rule. While we are calculating the derivative of f with respect to x, the last variable, is very important. If you're asked to do the derivative of f with respect to y, then it doesn't make sense to apply the chain rule. We just forget about it because that's not related. If we are to, that's the simple problem. if you want to calculate the derivative of f with respect to x, then in such a case you need to apply chain rule. So first the derivative of y with respect to y times first the derivative of f with respect to y, and f is y squared, and then the derivative of y with respect to x, and y is x cubed. Okay, and now if you do evaluate, this would be, first term would be 2y, and the second term would be 3x squared. And since we know that y is equal to x cubed, so I can substitute the value of y here, x cubed times 3x squared, and then this would be, right here, this would be 6x5, the answer would be. Okay, this is an example of using chain rule. All right, so this is all about the derivative. Now I would start with integration. First principle of derivation. So we did that yesterday. First principle of derivation. What do you want me to explain about it? Isa? Solve an example. Okay, we did that yesterday, didn't we? But let's do one more example. Let's, I think we did this example yesterday. Do you have an example in mind? For example, if you have x squared, f of x, using first principles, this would be what you would be doing. Now we know the answer from the rules that we learned, right? The derivative d of f over x would be 2x. Let's see whether we can get to that answer using the first principle. So the first principle says, let me just state the first principle here. X plus delta x minus f of x over delta x, limit delta x goes to 0. So let's apply this definition to this function, which is x squared. So once I substitute the value of x with x plus delta x, then I will get x plus delta x squared minus x squared. It is just the function as such, divided by delta x. Now if you open this square, you get x squared plus 2x delta x plus delta x squared minus x squared over delta x. This cancels with this, and you can take the delta x out. So this becomes 2x plus delta x times delta x over delta x. And sorry, I missed writing the limit, because I still need this here. Delta x goes to 0. Limit delta x approaching 0. Limit delta x approaching 0. And here, this delta x cancels with this delta x. And now I'm going to evaluate the limit, and limit delta x. Since delta x is approaching 0, this is going to be so small that I can ignore it. Okay. that I can cancel it or ignore it, and what I would be left with is 2x. This is an example of the ab initio, derivative by ab initio.
सर
जी
जी सर, ये हम इस बात को मैं कैसे करेंगे कि हम डेल्टा एक्स चूंकि जीरो अप्रोच कर रहा है तो हम इसलिए उसको इग्नोर कर रहे हैं, ये मेंशन कैसे करेंगे अपने सॉल्यूशन या प्रूफ में? हम ऐसे उसको कैंसिल आउट कर दें या कुछ स्पेसिफिकली लिखना होता है उसके साथ?
लिख दें. If you are descriptive about your equation, so you can write that we are taking the limit and we are ignoring the second term in the expression because it's small, is negligible because of the limit.
Okay, thank you.
Always write text around your equations to help. That's always very good and useful.
सर ये हमें डेरिवेटिव जो है इसको भी दोबारा मतलब इस पे फर्स्ट प्रिंसिपल लगाने को पड़ सकता है, जैसे मतलब वो जो 2x आ गया अगर उस पे भी हमने फर्स्ट प्रिंसिपल लगाना हो?
जी तो लगा सकते हैं.
सर वो आप एक दफा दिखा सकते हैं, क्योंकि वो मैं कर रहा था तो मुझे इसमें इशू आ रहा था.
क्या कर रहे थे आप?
मतलब उसका डबल डेरिवेटिव मैं ले रहा था, मतलब फर्स्ट प्रिंसिपल कर रहा था डेरिवेटिव पे कि उसका डबल डेरिवेटिव निकाल सकते.
Okay, bring whatever you have done in the office hours, okay, after the class, and then we'll discuss it.
ओके
सर एक सेकंड, आप पिछला बोर्ड इससे नीचे वाला बोर्ड दिखा सकते हैं before we move on?
जी
सर एक
सर
चीज
जी
पूछनी
करना
है.
वापस.
जी
सर आपने यहाँ पे 2y के अंदर 2y टाइम्स 3x स्क्वायर है ना, आपने y को x क्यूब से रिप्लेस किया है, हालांकि हमारे पास y ऑफ x की वैल्यू है x क्यूब.
हाँ
तो सर हमने y को कैसे रिप्लेस कर दिया इसके अंदर?
देखें, ये अगर है y of x क्यूब, ठीक है, तो इसमें क्या मसला है? y इज इक्वल टू x क्यूब. आई मीन देखिए ना, y की वैल्यू फाइंड करनी है आपने. दिस इज जस्ट अ नोटेशन दैट y इज to indicate that y is a function of x. Otherwise, it's just another variable. It's another variable which happens to be function of x. So it is the same if I write like this. ठीक है, तो मैं सब्स्टिट्यूट कर सकता हूँ, आप भी कर सकते हैं सब्स्टिट्यूट. एनीवन देखें ना, you can substitute the y with its value x cube, and that's what we did here.
सर अगर हम रिप्लेस ना करें और हम 6x square y लिख लें as our final answer, would that be a problem?
Gee, that's a problem because we are interested in finding out the derivative of f with respect to x. It's not a problem, but it's when you can simplify something, when you can get an answer in one variable, why have two variables?
Okay sir, ठीक है.
Okay, you're right in a way. This is it. So we have the variable, but since we know that y depends on x, ultimately in our calculation we would have to find y would always have to evaluate the value of x. अगर मैं यहाँ पे x 2 डाल रहा हूँ, x की वैल्यू 2 डाल रहा हूँ, तो y की वैल्यू क्या होगी बताएं अरवा? अरवा तो y की वैल्यू मुझे 2 यहाँ डाल के एवेल्युएट करनी पड़ेगी, इसलिए मैं ऑलरेडी उसको सिंबॉलिक फॉर्म में सब्स्टिट्यूट कर दें तो बेहतर नहीं है?
जी सर ठीक है, सर आपकी आवाज बैक करते हैं.
Okay, integral. To introduce the the integral, or we're going to use the example that we used last time. So last time we had a free falling object. We still have 15 minutes, right?
Yes, sir, 16 minutes.
Okay, so for a falling object, we figured out this relationship x of t is equal to cp squared, where c is equal to 5 meter per second. Just a warning. I'm trying to be as careful with units as I can. I'm always, whenever I write a quantity, I write units. For a physicist, we can't work without units, okay? And if you do not specify units in your exams, in your quizzes, in your assignments, you're going to lose credit. So be careful with that. Because a simple number in a physics equation or in an answer of a question does not make any sense. So this is what we did, and then we used the derivative. We took the derivative of this with respect to time, and that we define as the speed, and it was 2c t. And now v depends on t still, so then we did the double derivative, d squared x over dt squared, and we defined it as acceleration. That turned out to be 2c. Or then we recognize that it is nothing else but g, the gravitational acceleration. Okay. So you see, we go from position to speed using derivative, then from speed to acceleration using another derivative. Now, if we have the reverse situation, let's say we know the acceleration, okay, and we want to find out speed.
Excuse me, sir. Sir, why did we do the double differentiation? Like, why did we find the second derivative?
See this? So the time rate of change of the position, dx over dt is speed, and time rate of change of speed is acceleration. Okay? And then if I substitute the value of v in this term, these terms, it gives me the double derivative with respect to time of the position. So that is why we have double derivative appears. So we're just taking another derivative of this quantity, the speed. So first we took the derivative of position, we got speed. Derivative of speed gives us the derivative, the acceleration. But then you can recognize that v is nothing but v. So let me write it this way here.
Sir, I get that, but why are we doing this? Like, what was the main question?
Okay, let me just write the expression, then I'll answer. Okay, if you know that. Look, if you have the position time curve, okay?
All right.
Then how do you find the instantaneous speed?
Oh, I get it now. All right.
Okay, and if you have the instantaneous speed, how do you get the acceleration? Okay, and then if you're not interested in calculating the speed and you have the position time curve and you directly want to calculate the acceleration, you just take the double derivative of the position and you get the acceleration. Okay, so now let's say we have the reverse problem. In this case, we knew that x as a function of time, and we could calculate using derivative the speed and the acceleration. But let's say we start with acceleration. We know the acceleration, we want to find speed, or we want to find position. How do we do that? If we could find a way to if we could find a mathematical process that was the opposite of the derivative, you see, if we could go back from acceleration to velocity and from velocity to position, and there exists an opposite process of the derivative, and that's why it's sometimes called antiderivative. We can do or use the antiderivative to find x or to find v, starting with a. All right. So although the derivative has very fixed exact rules, antiderivative is a lot of guesswork. There are no well-defined rules, and it's not always guaranteed whether you would have whether you would be able to calculate the antiderivative of a function if a function is given to you. And one more thing. So when we have a derivative of a function df of dx, it is equal to f of x. Okay, and antiderivative is the process that you start with f of x and find f of x. All right. So since there are no fixed rules, and the derivative is a very useful concept, one thing what we could do is, whenever we have an f of x, we try to guess f of x first. We guess what would be f of x, and then we confirm by taking its derivative. And if it gives us this function back, then we say that this is the antiderivative. Small f of x is the antiderivative of f of x. Okay, we will do this with examples in a minute. Okay, is this clear? Somebody wants to ask question? Yes, Rafi.
सर theoretically समझ नहीं आया मुझे कैपिटल f of x और स्मॉल f of x में क्या फर्क है?
ये इसका डेरिवेटिव है. कैपिटल f of x is a derivative of f of x.
Capital F of x is a derivative of small f of x. Okay, sir.
ठीक है. And then when you go from, if you take the antiderivative, okay, I'm not using the symbol just yet. If you take the antiderivative of f of x, you should get f of x. But there is no formal way of going from capital F of x to f of x. So I'm telling, there is a hit and trial method. You guess what f of x is if you know capital F of x. Take its derivative, and if it brings you back to f of x, then your guess is correct. So this small f of x then is surely antiderivative of the capital F of x. Okay. All right. So I'm using this example, x equal to, now I'm going to use g everywhere. Now we know that's the value of 2c. gt square, okay? And the speed, the derivative of x over t is 2gt, and then the acceleration, which is double derivative, is just g. So this is half g, and then this would be gt, and this would be g, right? So this is the equation. Now we want to start with this equation. With this equation, and you know that I can also write this equation as dv over dt, the derivative of speed with respect to time, that is g, or the acceleration. So starting here, this is what we do with starting with x, and we do the derivatives gets the speed and the acceleration. So here we are starting with acceleration, and we want to find out v. Okay, so now this is the guesswork. So we try to guess a solution, a value of v, and then take the derivative and try to verify. So let's guess the value of v to be 1. Okay, and then let's take its derivative, dv over dt. What would be the answer?
0.
0. So this guess was not very good. All right. Okay. So, and actually, if I guess v to be any constant, is going to give me 0. So this, I cannot take a constant. So let me make another guess for v. So let's say v is equal to gt, and take its derivative, dv over dt is equal to g. Well, this looks like a good guess because it gives me this equation back. So that's mean my v is equal to gt, and we can see that here as well. So this is a good guess.
Sir, you can you repeat this guess वाला है वो कैसे करना होता है?
क्या कैसे करना होता है?
ये आप जो guess कर रहे हैं?
देखिए guess तो ये by practice आएगा ना, v की कोई तो शक्ल होगी ना v की, ठीक है? I'm first taking v equal to a constant and then trying to take its derivative, which gives me a 0, doesn't give me this expression, this value here. Okay, that's why I'm thinking of g to be something else. But let me.
Sir, we start with like the simple constant से फिर आगे जाएंगे and we keep increasing complexity, right?
देखिए जब आप बहुत ज्यादा प्रैक्टिस करेंगे ना डेरिवेटिव के साथ, ठीक है, तो then you will know कि guess कैसे करना है. If you take a lot of derivatives, then you will be able to make good guesses. Okay.
लेकिन हम तो इंटीग्रेशन से करेंगे ना, guesses तो like they don't work, right? हमेशा.
Well, this is one approach, and there are some rules about the integration, but guess also works. So a lot of integration is hit trial method. So you try different. You try the guessing method. You try some other. There are very well known. If there is for some functions or for some types of functions, then you know the integration by heart. You remember it, and then you just plug that in. But this is.
Would we learn the rules though?
Yes, we would learn the rules, but I'm just trying to explain it out to build it. But there is no systematic way of doing integration. Okay. So now this looks like a good guess, but there is more to this story. Now let's say if I change my guess, v is equal to gt plus a constant, and then take the derivative of dv. The answer would be G. So there is another good guess. Now, which one should we accept? The first one or the second one? This
The second one.
Yes, this is called the constant of integration, and I'll explain what it makes, what it means in our physical models. Okay.
Sir, don't we use C as a constant?
You can use C. I mean, the choice of variables. You are not grown up enough to not worry about the conventions or the choice of the name of the variable. Okay, so you could say K, C, whatever you like. I like using K. So V is equal to dt plus K. So the value of K depends on the physical situation of the problem, or what we call the boundary conditions. Or sometimes they are referred to as initial conditions. And I'll explain what that means. So let's say we choose this value, we choose this guess, B is equal to GT plus K. And now think about the problem that we are studying. So we have a free falling object, all right? And let's say in 10 seconds, so we start looking at the object, and and when it hits the ground in 10 seconds, t is equal to 10 seconds. And if I use this original guess, it tells me that if I substitute the value of t to be 10, where g is approximately 10, when this object hits the surface of Earth, its speed is going to be 100 meters per second. But what about this object is falling from further above? Okay, and we started our observation at this point in time. It already was moving, its initial speed was not 0. Then what would be its speed when it hits the surface of Earth? Now we cannot answer just using this equation. That's why this guess is better. Let's see. So what we do is we substitute t equal to 0 in this equation. Okay? And when we substitute t equal to 0 in this equation, this term is 0, and v at t equal to 0 is k. So that is our initial velocity, or when we start our observation. In some cases, in yesterday when we were discussing this example, we chose this velocity to be 0. That's why we were dealing with this simple model. But the more general case is because the object could be falling from before we start our observation. At time, for us, what is time 0, the object may already have some velocity, and that velocity is here. And if I can choose or change the symbol from k to v naught to indicate that this is the initial velocity at the time of observation, then this equation looks like v is equal to gt plus v naught. Okay. So now if this object was falling at 10 meters per second at the time we started our observation, what would be its speed when it hits the surface of Earth? Well, in 10 seconds, at the acceleration 10 meters per second, it would be 100 plus 10, 110 meters per second. Now this is more general. So that is why whenever we integrate, we have to introduce the constant of integration and then find it using the boundary conditions or the initial conditions. What was the physical situation when we started our observation that we are trying to explain? Okay, with this, thank you very much, and I apologize for the technical hiccup today. Hopefully that would be fixed tomorrow or by the next.
Sir, I have an unrelated question.